Curtis is going to step in and teach us some very cool things about fluid dynamics. Okay? Round of applause for Curtis, guys. Okay. Yes, I'll give you the microphone here. Okay.
Oh, hi, everybody. I'm Curtis. All right, so finite element methods. Have any of you guys heard of it before? Raise your hand. Okay, 2 of you guys. Okay, wow. So these are like a class of code that you use to simulate continuum physics, like things that kind of in the real world, right? So maybe you want to pursue a career in like rocketry, or like you want to analyze the thermal flow of rocket fuel or something, or if you want to go to like aerospace research or astrophysics, it's all over. So if you do anything in like the natural sciences, you'll probably find it. All right, so here are some examples. So the one on the left is like if you dropped food coloring in water, sort of. As you can see, this is like, we're trying to simulate this as accurately as possible. The one on the right there, on the top, that's like simulating an asteroid redirection program for NASA. This one actually got deployed in the real world. They actually rammed a satellite into an asteroid, not one coming towards Earth, but just to study it. The one on the bottom here is like stress analysis for if you're like a mechanical engineer and you're designing something. So all these fields end up kind of using these codes. Let's see, there's some more examples. All right. Have any of you guys heard of fusion ignition or like ICF? Okay, 2 of you guys. Okay. You guys have some learning to do, okay? So fusion ignition is a source of fusion energy. Basically what powers the sun, right? But we're trying to like capture that in an experiment. So it's been going on for like decades. Like so many people have tried to like get this working, right? And then in 2022, Lawrence Livermore Lab finally got something working where there's net positive energy. So scientifically, within the lab, this is theoretically a possible source of green energy, right? And so, yeah, somebody's definitely going to get a Nobel Prize. Looking forward to that. And so, yeah, I actually had the opportunity to work on that project there, basically the coding part, because they don't trust me with anything else. So this is the class of green energy. I guess the slide is green energy, if you guys choose to pursue a career in that. There on the left is magnetic fusion simulations. I'm guessing, like, if you guys watched Iron Man and like the arc reactor, I guess the arc reactor is like a fictional version of this. In reality, magnetic fusion is not there yet. You know, it's not like getting us actual, it's not a viable energy source yet. So we're losing more energy than we actually generate. I think this is called either a tokamak or a stellarator. Basically, you have plasma gas, and if you've taken physics 1 or 2, if you have a magnetic field over charge going, you could redirect where it's going. And then, so you have plasma gas going really, really fast, and then they start to collide into each other. And then there you go, you are starting to fuse some of the hydrogen isotopes. and then you get energy. So I guess the important part of this is that simulations is really important if you're trying to design these systems. So one of my mentors, his job is really to design experiments, run them, and see if they're viable. And then just like run a bunch of them, keep iterating, and then if they're good, submit a proposal to get a grant, get money, and try to get it fabricated, get an actual experiment going. So, yeah. Let's see. One more, I guess. So there's a really big code base called E3SM. It's for like modeling planetary sciences. This is ocean modeling. So if you're into like climate change and just like the climate sciences, atmospheric sciences, this is a really big code base that you might use. Search it up if you're interested. In the top right, we have a supernova. Like these, this class of code is used all over, right? So like, this is astrophysics, and I had another mentor who worked on, I think it was similar, like a similar supernova or something, and then he just changed fields. Okay, and then the bottom right is Rayleigh-Taylor instability. Basically, when you have two fluids of different densities and you put them together, they start to intermix like that. I would say like that certain instability is like a very well-studied type of instability. There are many others. And we kind of use it as like a base case to study your simulation package, see if it fails. Basically, if you're one of the developers for one of these code bases, you want to see how well it performs, right? So this is a pretty good way to measure it. Alrighty. Okay, quick history. I think you guys came to the right school. We all know the Manhattan Project, right? Right? Okay. Raise your hand if you know the Manhattan Project. Oh, awesome, okay. Now raise your hand if you're not paying attention. Oh, God. Okay. So basically in the Manhattan Project, in the early days, they would have some of the wives of the scientists would have to hand crank all these calculations by hand. And pretty soon they realized this is not efficient, right? You know, you have to feed them, and then, you have to feed, and then they have to take rest, and then, yeah, it's like hassle, right? So pretty sure they're like, dude, what if we use like better machines? So they bought some IBM punch card machines. They're using them, I believe they're using them right in the top left there. Yeah, and then imagine you're a guy named von Neumann. You're one of the most talented, you're a genius of your time. And then Oppenheimer, if you don't know, professor here, comes knocking on your door, and he recruits you. He wants you on your team to help in any way. And my golly, it's one of the best investments ever. Because the work he would do here would send shockwaves into the world, literally. And yeah, so I guess like as a side note, Oppenheimer, a professor here, literally probably like stood here 80 years ago, probably sat in a couple of your seats 80 years ago or 90 years ago. And, you know, just got this giant project together. Von Neumann, the work he started off as a consultant, and then like, he would like come so regularly that he started actually working there. And so he designed some of the earlier computers, one of them called the ENIAC, and that's one of the first computers possible, like, that could actually support some of these huge scientific calculations, right? And so he would do some other things, right? Like he would create the von Neumann architecture, which is the basic fundamental computer architecture that's running on every single one of your computers today. And he would also invent, well, I don't know invent, but like one of the pioneers of something called finite difference methods, basically allowing computers to solve partial differential equations. And yeah, his work would just create this wave of new simulations and computers and all sorts of goodies that we still use today. That's the Trinity test. As we know, that really changed the world. Not just like scientifically, like, oh my God, this is feasible, but like politically, like, okay, now there's like a new world order. And then also like in terms of like humanity, like there's like no going back from this, right? So fast forward decades, we used to do like underground nuclear testing in Livermore and Los Alamos. Now, since Clinton, we are not allowed to do any nuclear testing anymore. It would raise a couple eyebrows, I think. So we do something called stockpile stewardship, in which we run the simulations to study nuclear weaponry, but we're not allowed to actually detonate anything, okay? So that way we can still advance the field, keep our nuclear stockpile suited, but it won't cause any tensions in the world, okay? Alrighty. By the way, Oppenheimer's office is like 3 floors up, if you want to check it out. Okay, so von Neumann like pioneered this thing. So like we want to simulate the analog world, right? So unfortunately, computers can only do things discretely. So we're gonna have to cut up everything into chunks. And so as you can see, if I like continue coloring in this graph, it's gonna be like a really low resolution version of this flow field, right? And I don't really want that. I want this. I want something that's really accurate. So we will introduce some new methods to hopefully increase the accuracy of things. So there's 2 schemes, main schemes, and the Eulerian, you could sort of think it's sort of like what you're used to. You have a grid, and you would just imagine flow, like a fluid going underneath everything, and the grid stays constant. So you could calculate your differentials easily, just in between each grid cell. And then you have your Lagrangian. I like to think of this as like bubble wrap, where each of the bubbles are like self-contained. And like if, say, you have high density in one bubble, it starts to just push against the walls, and it just pushes out. So in this example, I have like high density in the lower left corner. And then like in the Lagrangian scheme, it would just push the cells outwards. I was trying to emulate the Sadov problem, which is literally a bomb exploding in the bottom left corner, which is also a common test problem. And so I think a good question to ask is why do this, right? So for Lagrangian, right, we want to like increase detail in areas that matter. So for example, in the bottom right, left, there's like a lot of like detail. Oh yeah, here, like, and so that can capture like curves well, right? Like you could capture areas that matter, while like areas that don't matter just are spread out more. And also Lagrangian is also very common in like solid materials, and it kind of makes sense because like materials themselves are kind of like bubble wrap. They expand and push against each other. Yeah. Okay, so finite difference methods, just a fancy way of like making our, go ahead.
Sorry, might not be understanding this, but for Lagrangian one, wouldn't it make more sense to have like the grid be more dense in higher density spots? Why is it that like the higher density spots kind of like expand so there's less resolution?
Yeah, it should be more like more grid cells in, so like your density like changes over wherever, right? We want to capture like the curves because that's like where it matters to get the most detail. So like if density increases rapidly, we want like to capture that curve. If like I had grid cells that are like really spread out, I'm not going to capture that change in density really well.
Okay, so it'd be like it's the change in density versus the density.
Yeah.
Okay.
Yeah, if I have like high density but it's not changing much, I don't care if my grid size is like really big. Like it's almost the same. Okay, so finite difference methods, fancy way of saying let's approximate our differentials. This is sort of Calc 1, I don't know. Oh, yeah, I think Calc 1. And so right here, I think the first equation we all know, right, is just pretty much what you learn in Calc 1. It's like just from, right? Okay, so if you're wondering how the second part is derived, that's just, both of these are kind of just the Taylor series. I just wrote the remainder stuff in the end. I think the most crucial idea here is that we've kind of gotten rid of the differentials. So on the left-hand side of both of these, there's no more derivatives we have to calculate. And so everything's just written in f, not f derivative or the second derivative. And so we can write our partial differential equations in just f. And it might be vague, but like if you look carefully, you could start seeing that, oh, this is actually kind of just a system of linear equations. So we could just do a matrix operation to get from one state to the next time step, and then to the next time step, and next time. It's kind of like a Markov chain. Not exactly, but we'll get to that, I guess. All right, so I'm gonna go through one example here, the heat equation. So imagine if you had like a bar, and it's a bar of raw, like a copper, I guess. And then it's insulated, so it's not interacting with the outside world. And then I heated it up so that it looks like that curve. So it's most hot in the center and then kind of cold in the edges. Okay, this is a well-studied problem. There's actually an analytic solution. So this is the heat equation, if you guys don't already know, and this is a partial differential equation. And you can solve this by hand, right? So like, you could work this out by hand. The solution is a Fourier series. If you are interested, just take Physics 89 or 110 or something. So let's now not do this analytically. We could try to make this discrete. By the way, the graph in the right-hand corner is how it like kind of projects over time. Like it starts out sort of cone-shaped. I can't really graph it at 0, but like, because it like just explodes. But like, just over time, it just like cools down, right? So let's make this discrete so that a computer can solve it. So let's make our discrete version of these partial differential equations. As you can see, both of these equations, or these expressions or whatever, I just stole from the other slide. So if you can see, sort of, I just took both of the what's on the left hand and then shoved it in there. We do truncate. Oh, my mom's calling. We do truncate the R term, the remainder term, and this is going to cause us problems later. So stay tuned, I guess. So I'm just like, I'm out there. So I'm just rewriting the this bottom equation here. And so I just want to make it clear that this is how we're evolving the states over time. We're taking everything with time step n, so n, and we're using that to calculate the next time step. And we did see a version of this in the Eulerian method from earlier. And I'm using U here, I guess, as temperature, but the idea is that you can use this interchangeably with other state variables, like maybe in a different problem, it could be density or pressure. In this case, it would be temperature. And so like, you'll probably encounter equations of states. Your most famous one is Pivnert, basically relating equation of states to other equations of states. And this is very useful. So like you could go from state to state to state. It's like you're taking snapshots to another snapshot to another snapshot. Okay, instability. So when we truncated our expression from earlier, we basically are introducing some errors into our code, right? It's not going to be super accurate. And so as you can see on the right here, things start to explode when we don't want it to. So to avoid that, the most fundamental condition that should be met is this bottom left. And the intuition here is that, if I have a bunch of grid cells and I, with velocity, like the fluid moving, and I specify the time step, I don't want it going more than how far my grid cell is. That means it's going faster than what I can capture. So for C max, it's usually like, it should be 1, but like usually we do like 0.9 or 8 just to be safe. Just so the ratio of how fast the shock wave or fluid is moving isn't faster than what we can capture. Okay, so some more instability. This is going, increasing time steps as we go down. And as you can see, it's just diverging. In this particular problem, we can write it as, I believe we can write it as a set of matrix operations. And for this particular problem, I think the von Neumann condition can be, it comes into play. Basically, we want our if you're familiar with Markov chains, we want our eigenvalues to be less than 1, or else things diverge. So, yeah. Okay, so we could extrapolate this to more higher dimensions. So this is like, instead of a rod that we heated up, this is more like a plane. And it starts off really perky, and then it just like becomes flat. And we just do the same thing, really. The only difference now is we have to change our way of calculating the gradients. There's a couple methods to do this. I didn't really want to put like a ton of math on the slides because I feel like that's not great. But we have like this one relationship, right? Intuitively, T current is like the temperature in the center of one of these cells. And then I take a directional gradient to the neighbor. So I go to the side there. And that's one relationship. So we do this for every all four of its neighbors. So we have 4 expressions. And so if we realize, oh, everything is known here except for the gradient of this curve, so we could just solve for that. It's just a linear system of equations. It's what we've studied for a long time, and computers are good at it. So there's also the Green-Gauss gradient method. So this is just Gauss's law, a version of Gauss's law, but I didn't put anything for it, so whatever. Okay, so if you guys are doing like fluid simulations for the final project, this might be helpful, maybe. So for fluids, at least in this example, we have an Eulerian mesh. So we have a static mesh of grid, and then we define the pressures in the center and velocities on the faces here. And we do this to prevent, we would run into instability again if we define the velocity in the center. Yeah. So just to sort of like zoom in here, the pressures, as you can see, it's common to like do this subscript notation where it's like, so this is just ij, and then to go to the next one, you just increment that index. And then to go in this in between, it's just half an index. So right here, you have the u velocity going to the right, I guess, and this u velocity going to the right, v velocity going up, v velocity going up, and then pressures in the center of each node. So that's how we capture, for now, fluid. And then, yeah, as we know, one of our state, if like we were doing gas, for example, we have the pressure and we have the volume. So we could just solve for T, and then if someone asks us what's the temperature throughout this grid, we can solve for that probably. Yeah, so since we defined the velocities at the faces here, to define like the velocity within, you just interpolate between the faces. So for this center one, you would interpolate between these 2 yellow dots, and then for these, for V, interpolate between these 2 blue dots. Cool. And then in the previous problem, we used the heat equation as our partial differential equation to get to the next time step. This time we're using Navier-Stokes. And this is you know, you could derive this from physics 1, really. Just, you're just summing the net forces. So you maybe vaguely see it, but like on the left-hand side, you have like some measure of mass and like acceleration. And then the gradient of P is a force. And then you have like just external forces. And then you have another sense of force that's from diffusion. This is per unit volume, so we've actually just divided out the volume here. Yeah, okay, that's all for this. Okay, so we're once again, we're gonna do kind of the same thing we did for the heat problem. So we have a bunch of state variables for each time step, and you could compute the pressure as a function of density. Actually, yeah, so like that's your equation of state. I think in different software packages, there are like, yeah, there's definitely, I think in astrophysics, there's a very different kind of equation of state. I think I showed it earlier, but I think it's directly proportional. And yeah, we use Navier-Stokes to update the velocity. We update the densities, and just repeat it. And then, once again, numerical instability. I feel like half the time your code crashes, and it's numerical instability, and like, you just pull your hair out. Because some of these simulations like just take so long and cost so much, and I get angry. So this is, I believe this is actually, I wanted to show another method. So this is right in between Eulerian and Lagrangian. So I moved the mesh a little bit, but not so much. It's called arbitrary Lagrangian Eulerian. And so this is some of the newer methods to simulate some of these fluids. Last thing, I think, I wanted to talk about animation meshes. Yeah, so like a lot of the people at like national labs who worked on some of these codes like end up at like Pixar, because like a lot of the work is kind of similar, or like it's along the same lines ish. But like the idea is like you're trying to change your mesh so that it captures what you want as best as possible. I think that is all for me, I think. Oh, there's this.
Thanks for being patient, guys. Make sure that you definitely get the attendance. If you have any questions, feel free to hang out afterwards. A lot of the stuff that we covered today is more just like to help you guys with ideas for your final projects. So if some of the deep cuts, like physics stuff, is a little more intimidating, don't be too worried. Like I wouldn't particularly expect that, I think, on your exams. Yeah. I don't think anybody's like that. We're not trying to be like sadistic to you guys, but hopefully it's informative. Hopefully it helps inform the directions you guys want to take your final project. Yeah, thank you guys for coming today. See you tomorrow. And yeah, if you have questions, feel free to hang out afterwards. Otherwise, get out of here. stop doing like I just said.
Yeah, I'm sorry, I just can't. How did you just steer the definition of derivative for like a solid half minute? It's like, dude, you're the physics major.
Oh, is that?
No, you were just looking at f of x plus delta x minus f of x over delta x for like half a minute. I'm like, dude, this is the definition of derivative, please. Say it!
Yeah. You know, there's something about like public speaking where like I was looking at like just the norm, right? And I called it sum of squares.
The
earlier.
magnitude of the difference. Like, that's it.
Yeah. It's something about public speaking makes you just like word mince in your head.
You
You know what
short
I mean?
circuit.
Yeah.
Okay.
Sorry.
Are you both like TAs or